So Greg is a recent postdoc, right? Joined
Yes.
us at TU Delft. He worked during his PhD to relate complex networks with water distributed networks, and I think this is the best way to introduce yourself. So welcome to Delft.
So
go ahead.
I'm Greg Kyritsakas. I recently joined TU Delft, working in a EU project for drinking water quality and the use of data. Before that, I was in Sheffield, and this is part of the work that I have done there. This is part of my work after my PhD, not exactly my PhD. Just keep this picture in mind. This is a picture of a whole system that a water company in the north of the UK has. It's their priorities. Complex system with a lot of treatments, a lot of different systems, a lot of different treatment works, etc., etc. This is the overview of the presentation. So just to explain to people that are not related to water, how is the water distribution network management done, how the water quality monitoring program works in water companies in the UK at least, and I think this is the same here. What is discoloration in the drinking water, and then we're going to the actual research, the aim and the methodology, etc. You saw the water distribution system. Ricardo explained it very well. Just quickly to explain how this is managed from water companies in order to avoid leakage, and also to understand better what is happening, to direct the drinking water and understand better drinking water quality. You have the treatment, you have then the service reservoirs, and the service reservoirs you have the distribution mains that are going, the distribution trunk mains that are going to the different areas. This area here, passing from the service reservoir up to the different distribution areas, is called water supply zone, because it's one zone that is fed by the same service reservoir or the same supply reservoir. And then, in order to control better what we have in the system, water companies, what they do is they change and direct the water from one pipe, where there is a DMA meter, as they call, which is called, in order to create small areas that are more controllable and that just have one access to the water. So you have, and these areas are called district meter areas. That's why I say DMA meter. So you pass from here, and then you have a distribution around the areas. See here, you see 3 different district meter areas. As regards the monitoring program, water companies are collecting data from, as you can imagine, to measure different water quality parameters from the outlet in the treatment. They do it every day. From the outlet of the service reservoir, they do it every week. And then they go randomly in houses, and they open the tap, and they measure, and they take a sample, and they go to the lab and measure the data. These are the main monitoring parameters, microbiological, such as the number of coliform bacteria. We have metals, such as iron, manganese, iron, manganese, aluminium, etc., etc. We have chemicals, such as, here we don't have that many, because in the Netherlands we don't use chlorine, for example. In the UK, where this is the case, we have chlorine as well. And aesthetic has to do with the color as a measure, or turbidity, which shows how looks the water. Now talking about discoloration. Discoloration is this thing. When you open your tap and you see this gray water, it appears in the drinking water because you have material moving with the water from the treatment up to distribution pipes. And once these material they are moved, then accumulate into the pipes, and then you have a sudden mobilization in the network. This accumulation includes materials such as corroding iron pipes. So you have like bad and old cast iron pipe. It starts corroding. You have material leaving from there. You have chemicals coming from the works. So whatever left from the works. You can also have it's related to what bacteria and material of bacteria in the pipes. And as regards the mobilization, this is the reason that these are moved suddenly in the network is because we have different hydraulic changes in the hydraulic condition, such as a burst that Ricardo mentioned before. You have a closed valve and you create changes in the hydraulic conditions of the network. The organic material, as I said, metals, organic material, usually pipe biofilm. An indication of discoloration when you measure high turbidity, and also you have a lot of high iron manganese. And one main thing is, remember, that's the main and major issue of customer complaints in the Western world. So people don't understand how good is the water quality, but once, even if it's not that harmful, once they see the open tap and they see this water, they start calling and saying that this is, we have this issue of discoloration. So the aim of this research was to, in the past, we have tried to investigate what are the relationships between the different water quality samples and how we can understand that with water quality, in terms of discoloration and other water quality issues. And then we tried, with this work, we tried to use these discoloration parameters in combination with complex network theory centrality metrics, and I'll explain a little bit later on, in order to understand how these are related, and also see which of the metrics could be used for analyzing distributed water quality, and finally, if this could be informative for water quality, for water utilities, for either the DMA level or even the pipe level of discoloration risk. So in the past, in order to do this, in the past, to understand the discoloration, in the past, we have the raw water quality samples. We imported into self-organizing maps. It's in a supervised maps, and then I will explain a bit later. And then we try to understand the correlation between water quality parameters and understanding also the causes of discoloration in the water distribution systems. Now, in this work, as I said, we use the raw water quality data in combination with complex network theory, imported into self-organizing maps, and try to explore the relationship between discoloration risk parameters and CNT metrics, and see if we have any CNT metric that could be valuable for us. The data that we used were from a water company in the UK. As I said, that one that you saw in the very beginning, this was the whole systems of them. They're serving more than 5 million people with water, and we took from them 14 years of regulatory samples taken from the taps from the period 2009-2022. These samples were distributed to more than 2,700 different DMAs. So the DMAs that I showed you before, like imagine that 2,700 of them. The main regulatory parameters were total chlorine, iron, manganese, etc. And then we used information from the GIS to understand, to import also the pipe characteristics of the systems and also the connectivity of the systems. So from treatment to water supply zones to DMAs. Finally, we included the customer complaints data set that the water companies have in terms of how many of these are in each pipe and in each DMA. Complexity of theory, and I'm going to go really fast on that. System that every system that's connected with nodes, and every system has formation in nodes that are connected, and they are connected to each other with edges. This obviously can be applied in water distribution systems because you have pipes which are the edges and nodes that are the end of the pipes. Have been used in the past, as in this work as well by Giustolisi et al., that creating some kind of metrics that give you an understanding of the complexity of the structure and understanding vulnerable points in terms of hydraulic loss. The most common are the node and edge between us degree, and node and edge between us degree, and node and edge between us and degree. Sorry. One simple example of one of these metrics, this is the edge between us and how this works. So assume that an edge between us of one edge is how many times a short path between the two different nodes passes from that specific edge. I have an example for that. So we have the edge 7, and we have 1 and 14 the nodes. So we have 4 short paths of 5 edges. This one, this one, this one, and this one. As we notice from the short paths, we have 4 of them passing from 7 and just 1 not passing. So the edge between us for that, for these 2 nodes is 0.75. We try to do this for all the systems that, from all the systems of, from all the water distribution systems of Yorkshire water. So we're talking about 70 water treatment works and 2,700 DMAs. And we calculated the metrics by doing one assumption that every DMA is a different water distribution system. The reason that we did that is because, as I showed you before, we have closed valves, and this system, the water is distributed directly there. And we created different metrics. Just showing here 3 of them that I have used in this work, which is the edge between us of the pipe itself, the 30 percentile edge between us of the DMA. So we calculated the pipe edge between us, and then we use the 3rd percentile of specific DMA to create the edge between us of the DMA, and the same for another parameter, which is the edge and degree. Self-organizing maps. Self-organizing maps is a supervised machine learning tool technique that clusters, as any supervised machine learning technique, clusters similar data. But the difference between this and other clustering approaches is that also creates correlations between different parameters. So it takes as inputs the parameters that you want, or the variables that you want to use. Each one has a different neuron, let's say, input, sorry, and creates plots where all the similar data are in hexagonic cell. So you see this small hexagonic cell here, and this hexagonic cell here, for example. But it also, once it finishes the analysis, it creates also everything that is plotted is not random. Everything that is plotted next to its cell is correlated to each other, and also everything that's plotted at the same exact position in its different plot are directly correlated according to self-organizing maps. So what you see here, you have 2 different parameters and a qualitative parameter, which is in months of the year. And you have what it actually shows is that when we have higher temperature, we have also higher number of sun size per hour. And also this appears in months of such as June, August, and July, which makes sense. So it's a very good visualization tool because you can see from that direct correlations between the others. So we have used that in the past in order to use all the data sets that we had and understand the correlations and understand how the systems work. And we try to use that here. This is the first result without using any CMP, and what we expected to see, and what we saw as well, is that we use a different parameters. Chlorine, this is a parameter about bacteriological activity. Just remember that it's kind of bacteria, these things here. Iron, manganese, and turbidity. So we noticed, and this shows that the SOMs work well, that whenever you have high iron and whenever you have high manganese, you have also high turbidity. We then introduced, we started introducing different CMT metrics. And what we found, and was interesting, is when we use the edge between us that you see here, all the other parameters the same. Again, the same correlation, and this is reverse. So we actually see that we actually notice that the higher the edge between us, the lower the iron and the manganese. This is, if you actually check if you remember what I presented before about the centrality metrics, that makes, and what is edge between us, that makes more sense, because you see that there is a continuity in higher water circulation in the pipes that they have higher edge between us, and you have, and that's why you have lower iron turbidity. We then again went to the pipes, and we introduced a parameter, and we introduced the pipe age, the pipe length, and the pipe diameter, and we found exactly the same. So whenever you have higher iron, you have low chlorine, you have small pipe diameters, small pipe length, and it's not related to pipe age. Again, reverse age between us shows this, but probably dead ends. Dead ends are at the end of the DMAs. So wherever you have small pipes that are going to the critical points that Ricardo mentioned before. We went again back to do that for the DMAs, and I'll go very quickly to this one, introduce the total length of the DMA, the iron again in the DMAs, the mean pipe age in the DMA, the mean diameter of the pipes in the DMA, introduce also what I explained before, what are the dead ends, how the total number of dead ends in that DMA. And what we've noticed is that again, iron is correlated with high number of dead ends and high number of high priority dead ends, something. But also, we have a reverse correlation of these with the edge betweenness of the DMA and the edge end degree of the DMA, which is very interesting. Last thing, we introduced, what you see here is the customer contacts that I said before. It's about how when they actually called and complained about discolored water. And again, I'm not gonna repeat all the parameters again, but you've noticed again that there is a reverse correlation between the edge betweenness, both the DMA and the pipe, with iron and also the customer contacts. As a conclusion, it's a lot of songs, and I had to struggle with to explain as well what is happening, but you have to remember that what we found is that there is a very interesting metric, edge betweenness, and also the DMA edge betweenness that shows that this one, whenever you have this higher, you have low having iron manganese turbidity in either the pipe or the DMA, which is a very good metric that water utilities can use to create a risk ranking list, let's say, of either the DMAs and the pipes. And now, once we did this analysis, now we're concentrating to creating other metrics, such as the short path edge betweenness, which is in the, what we calculated now was the connection between all the different nodes of the DMA. But we know in the water systems, we have one path. As we saw, there was a service reservoir. In this case, it's the DMA meter. And we try to create the short path between it, let's say, and also understand we have a lot of loops in the networks. And so sometimes a short path could be that one or that one. But the reality is that the water can go either that, always can go in both directions, but usually chooses the easiest one. So sometimes we've noticed that there are pipes that they're creating loops that are not that have a lot of stabilized water, let's say. So we're trying to find a metric that shows that into there. And based on these two metrics, we aim to create the optimal design of water distribution networks. And as acknowledgements, Professor Joby Boxall, Dr. Stuart Husband and Dr. Alexander Kazemi, we work together in this work in the Department of Civil Engineering and the Water Distribution Research